So hello, in this class we'll work out two problems on Euler equations. So the first one is this one. The thin circular disk of mass m and radius r is hinged about its horizontal tangent axis to the end of a shaft rotating about its vertical axis with an angular velocity omega. So this is a vertical shaft which is rotating with an angular velocity omega as shown, and here a disk of mass m and radius r is hinged here. So this can rotate about this x-axis. So this disk can rotate about this x-axis, and the shaft is rotating about this z-axis. So the thin circular disk of mass m and radius r is hinged about its horizontal tangent axis. This is the horizontal tangent axis x to the end of a shaft rotating about its vertical axis with an angular velocity omega. Determine the steady state angle beta. Assumed by the plane of the disk with the vertical axis. So this is the vertical axis, and the angle made by the plane of the disk with the vertical axis is beta. Determine the steady state angle beta assumed by the plane of the disk with the vertical axis. Observe any limitation on omega to ensure that beta greater than 0. So here, this is for this disk. This is actually rotation about a point, and that point is this point of hinge. So the disk can be taken as rotating about this point. So if you draw the projection of the disk in the y dashed z dashed plane. So this is x, this is parallel to x, and y is perpendicular to this plane. So this is y is perpendicular to this plane. So x is coming out of this, and from this and about this x we give a rotation beta. So we get y dashed and z dashed. Okay, so about this x we give a rotation beta, so we get this and this. So this is x is coming out of the paper. X and x dash are same because we are giving rotation about x. This is x, and we are giving rotation beta about x. So x is coming out of paper, x dash is also coming out of paper, y is this and z is this, but after giving rotation about x, y goes here, y dashed, and z goes here, z dashed, and this is the plane of the disk, or the projection of the disk on x, on yz or y dashed z dashed plane. So and what is the free body diagram of this disk? Here there are reactions Rx, Ry. This should be Rx, Ry, and Rz. These are the reactions. This is Rz dashed, this is Ry dashed, and Rx dashed is coming out of the paper. So these are the reactions coming on the disk from the support. Here there is one mistake. This should be Rx dashed, Ry dashed, and this is Rz dashed. And here the weight of the disk working through its centroid. So we have to apply the Euler's equation about this fixed point, because this is rotating about this fixed point. Even this rotates and this rotates, this point is fixed. So this is rotation about a fixed point. So ix dashed x dashed, that means ix dashed x dashed is I xx plus mass into r square, mass into r square. Iy dashed y dash is half mr square. This is Iy dashed y dashed is half mr square plus mr square, and Iz dashed z dashed about this. Iz dashed z dashed is 1/4 mr square. And so what is the angular velocity of the disk? The angular velocity of the disk is omega about this z, omega about this z and nothing else. So omega about this z means minus omega sine beta, omega about this z. So this is cos beta along z dashed, so cos beta along z dashed, and minus sine beta, cos beta along this is omega, so omega cos beta along z dashed and omega sine beta along minus y dashed. So omega y dashed is minus omega sine beta. So this is the Euler's equation. Here all x's should be replaced by x dashed, y's should be replaced by y dashed, and z should be replaced by z dashed. So here our inertias, and all this omega x dot, omega y dot, omega z dot, they are zeros. So the first terms in all three equations are zeros, and here omega x dashed is 0, so this is 0 and this is 0. So this equation is right hand side is 0, and for this equation also the right hand side is 0, and this moment is actually about x-axis. So we are interested in the first equation. In the first equation, omega z is this and omega y is this, and izz and iyy, izz z dash z dash, iy dash y dash. If you put the values, then omega x dash is minus omega square sine beta cos beta into zz 1/4 minus 3/2 mr square. So this. Now what is mx dashed? Mx dashed is the moment applied on the disk, moment about this point which is working on the disk, applied on the disk, applied, that is the moment due to the external forces, that is the weight here. So mg multiplied by r into, this is beta, mg multiplied by r cos beta. So this is mg multiplied by this, oh sorry, this is r, this is beta, so mg multiplied by r sine beta, mg multiplied by r sine beta. So mg multiplied by r sine beta is this, so cos beta is this. Now as cos beta cannot be greater than 1, so the right hand side has to be less than 1, and this is one condition, that 5 omega square r should be greater than 4g at least. And another solution is beta equal to 0. When beta equal to 0, then only this component remains, this is 0. So here this component remains omega, this is 0. So all these right hand sides are also 0. So mx is 0, and when beta is 0, so if this is not there, this moment term is not there, mx is also 0. So beta equal to 0 is another solution. So now we move on to the next problem. So this is the next problem. Here a uniform slender rod of length L. So this is a uniform slender rod of length L is welded to the bracket. So this is a bracket and it is welded to the bracket. So this is like a built-in end and bracket at A. On the underside of the disc B. So this is the disc B, This is the bracket, this is the disk B, and the disk B is rotating about this vertical axis with an angular velocity of omega. Now the disk rotates about a vertical axis with a constant angular velocity omega. Determine the value of omega, which will result a zero moment supported by the weld at A for the position theta equal to 60 degree with B equal to L by 4. Means when B equal to L by 4 and theta equal to 60 degree, then for what omega there will be no moment reaction on this slender bar at A. Okay, so the uniform slender rod of length L is welded to the bracket at A on the underside of a disc B. The disc rotates about a vertical axis with a constant angular velocity omega. Determine the value of omega, which will result in a zero moment supported by the weld at A. So the moment at the weld will be zero. The moment at the weld at A will be zero. Now from the geometry, if theta equal to 60 degree and beta equal to L by 4, if we call the center point as O, then the center of mass of this slender bar, which is at the middle of the slender bar, is directly under O. So the center of mass is directly under O, though in this figure it is little shifted, but it should be directly under O. Now this is the free body diagram. Here we are showing the moment in blue. This is the moment. So but the moment should be zero, and these are the forces. So all reaction forces will come in this direction, and the direction coming out of the paper or going inside the paper. This is perpendicular to the plane of the paper. So this here, this is y-axis and this is z-axis, and the x-axis is coming out of the paper, and we give a rotation about this x-axis by an angle theta. So y dash become parallel to the bar and slender bar, and z dash becomes aligned with the slender bar. So y dash is perpendicular to the bar and z dash is along the slender bar passing through its centroid. Okay, so here it is better to take moment about A, but because why is it better to take moment about A? Because these reaction forces will not have any moment about A, but A is neither a fixed point nor is it the center of mass, so we cannot take moment Euler equation about A. We have to take it about the center of mass. And if we take moment about this, then these reaction forces, especially these reaction forces and the reaction forces coming out of the paper or going inside the paper, will have moment about the center of mass. So for that we have to also solve the force equation to get the reaction forces, and to get the force equations we need the acceleration of the center of mass. So what is the acceleration of the center of mass? Acceleration of the center of mass is acceleration of A, the point A, plus acceleration of the center of mass with respect to A. So this is the acceleration of the point A plus acceleration of point G, that is the center of mass, with respect to A. So acceleration of G with respect to A is alpha cross AG, and alpha is 0 because here there is no acceleration. Here there is no acceleration. So this is 0. So this is omega cross omega. AGA is this alpha cross AG plus omega cross AG. AG is not having any acceleration, angular acceleration. So this term is 0. Now if you add these two terms, then this is omega cross omega OA plus AG, which is OG, and OG is this. So omega cross omega, omega is also along this, omega is along this, and OG is also along this. So omega cross OG, this is 0. So the acceleration of the center of mass is 0. So now we can show that if this is W, then the reaction coming here is only R, which is equal to W. So now we are in a position to take moment about this center of mass, and about the center of mass, these are the inertia values. Since it's slender, we are assuming that the moment of inertia about z dash is 0. So here, and all the dot terms are omega x dot, omega y dot, omega z dot terms is 0. So these first terms are all zeros, and you have to remember that z is actually z dashed, y is actually y dashed, and x is actually x dashed. Omega x dashed is 0 because here omega is only about z axis, and if you take component, it will have components along y dashed and z dashed. So omega y dashed is there and omega z dashed is there, but omega x dashed is not there. So omega x dashed is not there, and omega y dashed is omega minus omega sine theta, and omega z dashed is minus omega cos theta. Why? Because omega is along this, omega is along this. So if you take component along this, and if omega is, so if omega is along this, then this is omega cos theta, and this is omega sine theta. Omega z dashed is omega cos theta, and omega y dashed is omega sine theta, is omega if omega is along positive z. But if omega is along negative z, then these would be negative. So these are the omega values. Now all these equations, this will give you 0. The second equation and third equation, the right hand side is 0, and nor is there any moment about y and z axis. So only this equation is coming. So mg x dashed equal to this. So, and what is mg x dashed? Mg x dashed is this w multiplied by this length, and that means this length. This length is L by 4. So it's mg L by 4 is this, and omega square is this, and omega is this. So another interesting point which I want to mention here, that you can take moment about center of mass for m equal to h dot. You can take, for m equal to h dot to be true, you can take it at center of mass or any fixed point. So about center of mass or about any fixed point rotation, m equal to h dot is true. Now if you want to apply it for any arbitrary point, then what you have to do, in place of, suppose you want to apply it about any arbitrary point q, then with mg, for this mg you'll always use hg dot, but along with that, if you want to take mq, this additional term has to be used. Okay, why is this? Because mg means, mg is rho 1 cross f1, rho 2 cross f2, rho 3 cross f3, like this. And what is mq? That is r1 cross f1, r1 cross f1, r2 cross f2, r3 cross f3, and r1 can be replaced by qg plus rho 1. R2 can be replaced by qg plus rho 2, and this r3 can be replaced by qg plus rho 3. So mq is this. So this is qg cross this plus this. So this is same as mg, and this is summation of forces. This is mass, total mass into acceleration of the center of mass. So this is the thing. So here also we can take moment about A. So moment about A is moment about G plus ag cross mass into acceleration of the center of mass. So mass into acceleration of the center of mass is 0. So here ma equal to mg, and we can take moment about a same as moment about g. So what is moment about g? The same as what we are getting here, moment about g. So the right hand side is same, and in the left hand side we are taking moment about a. So mg multiplied by this, going inside, so negative. So this is minus mgl by 4 equal to this, and from here you get directly this value of omega. So it is required to take moment about a because we want to avoid the moments of the reaction forces. If you can take moment about a, then the moment due to the reaction forces at a will not enter the equation. So you can take the moment about a, but with the Euler equation terms you have to add this. But in this case, fortunately, since the center of mass acceleration is 0, so this term has not got no meaning. So the Euler equations coming from this you can use same as this you can use same as this, and the left hand side you can use ma also. So ma is minus mgl by 4. So these are two example problems which we have discussed in this class.